Raro, no se ha despegado. Aló, buenas tardes. ¿Qué tal? Eh, bueno, sí, lo puedo buscar. De hecho, ¿cómo que se llama ahorita quien dirige? Pues, Johnny. Johnny fue el que me sugirió que hiciera el cambio. Creo que le había enviado ese comprobante a él. De todas maneras, correcto, sí. Ajá. Sí, ajá. Creo que eran $30, $35, algo así por ahí. Yo lo puedo buscar de todas maneras. ¿A quién envío el comprobante? Ajá, ok, de acuerdo. Sí, seguro. Yo, gracias. Hasta luego. No se ha conectado nadie. A ver. ¿Será que no se las puse? $803. Ay, ay, ay. Ok, ya van 2 veces que no le he puesto esto.
Buenas, profe.
Buenas, disculpen que me equivoqué de link.
Sí, ya les aviso a los demás.
Sí, ok.
Buenas tardes, profe.
Buenas tardes, disculpen con la confusión del link.
Ya, no hay problema.
Mientras esperamos a los demás, vamos a agregar aquí la clase de ayer, que fue por eso que me confundí. Ya llevamos 4 personas. Mañana tenemos una reunión del decanato con los estudiantes convocada por los dirigentes estudiantiles. Es que yo les hice llegar a ellos el link, si alguno de ustedes se quiere unir también.
En mi caso, yo tengo clases a las 10, profe.
A esa hora, ok.
Sí, yo no voy a poder. Pero sin embargo, creo que ya hice conocer mi punto de vista al representante.
Ah, perfecto.
Pero
Okay.
sí, espero que así se considere.
Hicieron encuestas nuevas, porque la encuesta que tenemos es de la semana pasada y no sabíamos si eso había cambiado un poco.
Ahorita está él haciendo otra encuesta, sin
Ajá.
embargo hay varias correcciones que se le está haciendo de cómo se planteó la encuesta.
Ok.
Pero bueno, vamos a ver qué pasa ahí.
Seguro. ¿Alguna pregunta del material mientras esperamos que sea? Pues vamos a esperar por un estudiante más y empezamos. ¿Cómo van con la tarea?
A mí me faltan los dos últimos aún.
Ok.
No he terminado.
Entonces, que para el próximo lunes tendrán todos los ejercicios.
Yo creo que sí, para el lunes estaría súper bien, profe.
Así puedo poner una nueva tarea ahora. Bien, ya está actualizado el Moodle.
Profe, disculpe, ¿puede repetir lo último que dijo? Es que justo ahorita me llamaron de bienestar a ver si estaba bien aquí en la U y no escuché qué dijeron.
Ah, sí, no, que hemos tuvimos otra reunión con Cancillería para interpretar un poco. El CES mandó hace una semana unas disposiciones de flexibilización de las actividades académicas y entonces queríamos interpretar esa flexibilización para ver cómo la podemos usar para nosotros, ¿no? Pero teníamos el problema de que muchos estudiantes no se estaban manifestando, no habían dicho si tenían problemas de conexión, si tenían algún otro tipo de problemas de salud o problemas de condiciones de trabajo en sus casas, ¿entienden? Entonces, se propuso esta mañana hacer una especie de campaña, Conéctate o algo así se llama, para contactar a todos los estudiantes y ver si tenían, en qué condiciones estaban recibiendo clases virtuales, ¿no? Entonces yo creo que eso es parte de ese esfuerzo.
Ay, qué chévere.
Entonces mañana vamos a tener, como decía, vamos a tener una reunión con los estudiantes para explicarle un poco, interpretando por lo menos lo que sabemos hasta ahora de esas disposiciones y qué podríamos hacer con el semestre, dependiendo de qué fechas se reanuden las clases presenciales. Y entonces, bueno, y que todo el mundo ventile sus preocupaciones y sus dudas, pues, ¿no? Bueno, vamos a ver aquí. Ok, yo creo que ya podemos empezar. Entonces vamos a compartir aquí el pizarrón. De acuerdo. Entonces, yesterday we were discussing the lowest order diagrams we could have in the expansion, okay, in our one particle Green's function expansion. Okay, so one particle Green's function. Expansion. Okay, so remember that we have these ingredients. So you take it like a, you know, a cooking exercise. Ingredients. Okay, we have the full propagator. Okay, we have the free particle propagator. Okay, and we now have the two particle interaction, okay, which is this diagram here. Okay, and this was minus I over 2B KLMN, okay, MN, okay, and going out KL. Okay, so we have these ingredients here, and now we must combine, sorry, what did I do here? So we must combine these now to generate an expansion. So remember, we like to do this diagrammatically. First, we're going to do this in KT space. So let's put here KT space. In the case of the full Green's function, we can have K2, K1, and then T2 minus T1. Okay, and here we will have something, this is associated with K, so we have K, T, T2 minus T1, okay? So this is KT space.
Profe,
yes?
If I am not in a mistake, the two lines with the arrow pointing to the right,
Yes.
Is in the Fourier space?
No, you could have the arrow. Depends on what labels you put on the ends, right? So if this is K1 T1, K2 T2, this would be in KT space, right?
Yeah.
If you in Fourier space, then you have you would write something like this, right? K2, K1, and omega, right?
Oh, yeah.
Right, and you would still have the propagator, but you would have the Feynman rules associated with Fourier space. Okay.
Okay. Thank you.
Okay. So we have these ingredients, and now we have to combine, as we did with the one particle interaction. Now this is a two body or two particle interaction, two body interaction. Okay. And now we must combine these ingredients in order to generate an expansion. Okay, so we generate an expansion in orders of the interaction. Okay, generate an expansion in orders, okay, of the interaction. Okay, so the interaction is this wavy line here. So we will have as before. Okay, we will have as before. We'll have something like this. So we have the full. Okay, again I put KT space. So we will do again the exercise of Fourier transforming. So you see that when we do a more realistic expansion like this, we still have the fact that we have a translational invariance of the interaction. So K omega space is gonna be a nice space to work in. Okay, so this again will be the first, the lowest order propagator. And yesterday we were seeing that the lowest order we can have next to the zero, this will be the zero order because it contains no interaction. Okay. Zero order, just so you know some of the language, no interaction. And then the lowest order interaction is just going to contain a single term like this, okay? A single interaction. So we suggested that the lowest order interaction would be something like this. We had a loop, okay? Then we'll continue here. And we have that the arrow following here should be in the hold direction. Remember that the positive direction to the right would be propagating forward. So these would be free particle Green's functions here. And this is going to be propagating back. So this is going to be a whole Green's function, or an advanced Green function, as in another language. Okay, so this was going to be the tadpole diagram. Okay, and if you can come up with a diagram which is also first order, which would be more important, and we'll see how we judge whether the importance of this diagram, okay, referring to the matrix element that is involved by this interaction term, then I would be very interested in discussing that with you. So if you have any suggestions for other types of diagrams of the first order, which are not either of these two, so the other one was going to be the half oyster diagram, where we have a wavy line here, and then we have a back propagating a propagator going like that, okay, and then it goes like this. So here we have K, okay, going in here. We have an internal loop, which we should label with an L, okay, and then we have another K coming in here, okay, coming out here. So we know that when we have a very simple diagram like this, we have no flow of momentum in this direction. Remember, we were assigning, so we remember the conservation of momentum. Okay, and we'll see that when we Fourier transform. Requires that then, if I go into here, okay, into this vertex, and then this, in principle, I could have momentum going away into this interaction, into this hole, but then this hole is created and destroyed, so the momentum is returned over, so that the end product is that we're going to have an outgoing propagator with the same momentum. So here we would have a Q equals to 0, okay, a transfer of momentum. And here the same, we have this will be a G naught, okay, this will be a G naught plus, okay. Again, we have an internal variable here over which we have to sum, and this outcoming and incoming. So we know that the outgoing energy must be equal to the incoming energy, okay. So this must be both of these should be K. Let me draw this L a little more comfortably there. So you can erase this guy. Okay. Okay, and we have L here. Okay, so these are all the vector quantities here. Okay, and this is the oyster diagram. Okay, so, and then you can go further, okay, and then you start getting second order diagrams. Let me just give you an overall picture, and then we will address these diagrams in detail, okay? So what else could we have then? The second order diagram without any labels, okay? It could be something like this. This would be a contribution. And then we have another interaction here. Okay. And then we could have three tadpoles, but then we can have a combination of a tadpole and an oyster. Okay. Okay. And these might come, you know, first the oyster and then the tadpole. So we could have a combination of these two, and so on. Okay. And we could have a square of the oyster, and then we could have some more complicated ones like we saw yesterday also, which was a diagram which is something like this. And then we have a particle hole loop. Okay, and higher order diagrams. Okay, so you see that the tadpole and the oyster are going to be the lowest order in the interaction in this expansion. Then we have second order, then we can have third order, and so on. Then we can combine this polarization diagrams, that we will call them later, combined with the tadpoles and the oysters and so on. Okay, and okay, so all possible diagrams. This is the spirit of Feynman, the Feynman expansion. Okay, so let's focus now on the tadpole and the tadpole and the oyster diagram. So let's create now a new page. Okay, so let's see in KT space. Okay, KT space, what does this diagram look like in terms of equations? Let me draw it a little bigger so you can see. Okay, so we have K T1 and K T2, and then we have the intermediate L, okay? And this occurs at time T, the interaction. So this will be the scenario for KT space. So we know that this interaction could have happened anywhere in between T1 and T2, and then the momentum of this hole could be anything, okay, from as long as it's below the Fermi sea, okay? So as I drew at the end of last class, then we have a factor here I would emphasize, I'm not going to put in yet, that this is a contribution of the fermion loop. Okay, and then we have a sum over the internal labels here. So one of the internal labels is L, and this must be smaller than the Fermi energy. And then we integrate over all possible times, intermediate times. So we have here from minus infinity to infinity, okay? And then we draw the first propagator, which will be this one. So this would be I, G naught plus, okay? And then K of T minus T1. Okay, that's the first propagator here. Then we have the interaction. So let me multiply it by the interaction minus I halves B, let's just put it like this, K, and this will be, you see, here, let's draw the interaction here, okay? So notice that in this diagram, as I have chosen for this leg K, okay? Remember this is R and this is R prime, okay, in the matrix element. So K and K goes out, and then we have L, and then we close this one like this, okay? And the arrows going outward here, so we have this, right? So for the R, okay, remember that this was K, let me put the general case, KLMN, okay? So this must be the input. So the first one is R. So the input K on the side R is K. Okay. And then we have the other input is going to be this guy here. So this is going to be L, is going in, so it's an input, okay? So this is going to be L, okay? And then we have also going out, now going out, this other K in R prime, so this will be K again. And the other one going out will be this one, which will be L. So this is the VK, L, KL. Is it clear? Sorry if I should have put K prime, L prime, M prime, N prime, so that this would be generic, and then we choose, okay, from the main diagram, which should be like this, from the generic diagram, okay, and we have M, okay, going in, going out, okay, and we have a M, N, K, L. Primes. Is this clear? Okay, how I chose this, because the choice, the combinations of labels here will be very important in determining the matrix element. Okay, so this will be just the generic interaction, but once we choose these legs to be K and these legs to be L, then we have this combination here. Okay, so now we use the interaction here, we drew the interaction, now we draw this other propagator here, which is propagating in the negative direction, so this will be minus I G naught minus, no, this will be plus, okay? Okay, and this has momentum L, and this goes from where to where? So this is T, this happens at T, so this would be T minus T, the ending minus the beginning, okay? So we drew this propagator now, and finally we have this propagator going out. So we have, put it here, I, G naught, and this is propagating in the positive direction, so it's G plus, and then we have K, okay, and T2 minus T. Okay, so this is it. This is the full expression, save for one additional, and I told you this was the last rule we will include in the Feynman rules, is that each time we have one of these loops that we hadn't seen before, they imply a minus sign here. So each time you find a fermion loop in the diagram, you should put a -1 here. Okay, so this is how it works. This is how I translate, okay, translate a diagram into equations in KT space. Okay? So let us, we know the forms of these guys here, the G plus, we know how they look in KT space. We derived that early in this section. And we also know what this looks like. We wrote the prescription for G naught. So the last thing I'm going to put in this view graph is the value of I G naught. So if you look back at your notes, I G naught minus of a L and T minus T prime, T minus T is going to be I, this I here, times the value of the propagator, which involved another I, and epsilon, exponential of I L over H, T minus T. Okay, so what is this? This is 0. So this is 1, and this just gives me another -1. Okay, so this here is going to be a -1. Okay? Let me draw this with another color. It gets emphasized. Okay? And this is coming from here.
Teacher,
Yes?
can you repeat why we have two eyes? Please.
So this we saw in a previous class. We derived the form of the Green's function. Okay, so we said that we derived the explicit integral for that, and we said that G0 minus was this. So let me put it like this. So this guy is this guy. Okay, so this was I theta t minus t, right? So we had a theta here, okay, but theta of t minus t, we assigned 1 to that, okay, so this is 1 here, okay, and then we have this exponential. So this I corresponds to G0 minus, and then we have the I additionally that we have here, and that's why we have two I's, okay?
Yeah.
Okay, good.
It's like G naught minus is independent of time.
Yes, G naught is not independent on time, but it's evaluated at zero time interval. Okay, it's like evaluated not in a particular interval, but at the zero interval. Okay, so this loop will be a zero interval because this happens in zero. It's like it happened in zero time. You emit and you absorb you emit at time t and you absorb at time t. So this is like an instantaneous process, okay? And that's why, fortunately, we get a definite value for the propagator in that case. It's just a factor of -1.
Okay.
Okay. Okay.
Yeah.
So let's Fourier transform this. Okay. So we use our regular definition of the Fourier transform. Okay, and now in Fourier space, okay, we get now that this is going to be equal to -1. Okay, then we have the summation L smaller than KF. Okay, then the integral minus infinity to infinity dt, and then we get, I'll put the I here so we don't forget any terms, and then we Fourier transform. Okay, and we have this function here, which is in kt space. I'm now going to put in k omega space. So in k omega space, this is d omega 0 to infinity. Okay, and then e to the minus I omega, and we put the time, so it's the final time minus the initial time, and then G naught plus K and omega. Okay, that will be the expression. Then we continue here. This will be minus I. In a second, I will explain why we have this factor of 2. Okay. KL. Then we have the -1 due to the advanced Green function. And then we have another factor of I. So it cannot be more explicit than this. So 0 to infinity. I'm going to use another label here for the frequency. And then minus I omega prime T2 minus T. Okay. And G0 plus K and omega prime. Okay, so that's a full expression again. Let me I fudged the K a bit. Yeah. The notes are clear. Okay. Okay, so we did an exercise like this before. So I'm going to put the two minus ones here. Okay, two minus one together. Okay, just so we keep track. This minus one's coming for the fermion loop. Fermion loop. Okay, well, this one is coming from the Green's function evaluated at the same time. Okay, and then we have here we can put the summation. Okay, which we will not do for the moment. Okay, and now I'm going to put together. I'm going to push this this integral of time. I'm picking up all the terms that depend on t, okay? So we will end up with the following expression. So we have the sum, now we can put here the interaction, minus I over 2, VKL, KL, okay? Then we have two factors of I, so I put I squared, just to keep track of all the items in the expression. And we have one integral, two integrals of omega from 0 to infinity. Okay, I'm doing both integrations. Okay, just to save some notation. Okay, and then we put everything that doesn't depend on t. So we have I omega t1. Okay, minus is t1. Then we have I minus I omega prime t2. So this is this one, and the rest will be in the under the integral of time. So we have the integral in time minus infinity to infinity. Okay, so it's important to at this point. I'm missing something very important here. We will have, let me erase this. Okay, so here we'll have the two Green's functions. You see that they don't involve any time. So we'll have a G naught plus of K omega, okay, and G naught plus, okay, times G naught plus of K omega prime. Okay, so these will be these two terms. And then finally, we'll have the integral over time minus infinity to infinity of e to the minus I omega t e to the minus omega plus I omega prime t. Okay, so this we can put together. Okay, e to the minus I omega t, sorry. So our common factor is going to be t omega minus omega prime. Okay, that's going to be this. And what is this integral here? This is going to be delta of omega prime. Okay, so this we can do independently of the rest of the integrations. Okay, these two omegas are just fixed. I know that we're integrating these here, but now this is requiring that both these omegas are the same. Okay, so let's now apply this delta into this expression. Okay, any questions here before I change? Okay, so I'm just pushing the t integral through all these integrals and picking up all the terms that involve the variable t, okay? And I put them all together here, and it turns out that we can do now the t integration, and we get this delta omega prime. Okay, so once we apply that delta, we simplify the expression to the following. So we have minus 1, and we have the I squared, we have the L smaller than KF, okay? And then we have minus I over 2, okay? KL. Okay, and with the delta, we eliminate one of the frequency integrations, so we're left with just one frequency integration, and we can write then our the remaining exponential like this. Okay, and then we have, let me put it here so it fits nicely, K omega. Okay, and notice that we apply now the condition, and we get just the same factor of the Green's function twice. Okay, so we have, this is an integration. We have to do this integration here. Okay, but notice that on the other side of the equation, this is just the first term in the Fourier transform of the full propagator. So the full propagator, what's it going to be? The full propagator, okay, was going to be in KT space was G, K, T2 minus T1 in KT space. And the Fourier transform is the omega 0 to infinity, then e to the minus omega T2 minus T1 of the Fourier transform of the full Green's function. Okay, so notice here that we have the exponential, we have the same exponential, okay? And so, and we have the integration, a single integration. Of course, we could call this omega prime, okay? It's an internal variable, so it's a dummy variable, which we can call it any way we want. So in particular, it could be the same frequency. So we have this multiplied by the exponential. So we can now assign, okay, in Fourier space, again, we did this once before, okay, in Fourier space, this will look like this. So the tadpole diagram, see if I can draw some straight lines here. Now it's going down. Okay, the tadpole diagram in K omega space. Okay, this would be now K omega. Okay, and K omega on this side, and we have an internal loop here. Would be then just the kernel of this interval, because we're now expressing the full Green's function in K omega space in terms of any of the K omega space in this case. So we eliminate this integration and this exponential factor, and we get that this is going to be minus times minus. Okay, so this is a plus 1. Okay, due to this product. Then we have we took out the factors of I. So let me reunite the I's with the G naughts. Okay, so we have L smaller than KF. Okay, and so we have the interaction KL. And then we have two factors of G naught plus K omega. Is this clear? So I put the two I's here. I just put them back into the Green's function. So with that, we can have Feynman rules in terms of IG0 instead of just G0. Okay? Any questions about this? Okay, so we can turn, yes, it's okay?
I have a question.
Yes.
I think you mentioned 3 classes ago, but I want to know why you are using the limits of the integral. For
Yes.
omega and for t is different. We have from minus infinity to infinity and from 0 to infinity. Why we are doing
the t's, because remember the t, we have advanced and retarded Green's function. So the time, we want diagrams that can go back in time also. So this is between minus infinity and t infinity. Now the omega is going to be some energy. So it's going to be associated with an energy, okay? So the energies are all positive in this case. So the omegas are only between these in this range. Okay, we have some rules for the G pluses and G minuses so that they can be from minus infinity to infinity. So we have past and future, but the omegas are all going to be positive definite energies. Okay, this is just a matter of that we call the excitations. This will end up being the what do I call this, the energy of the quasi particle. Okay.
Yeah. Yeah.
Okay. So this is why it's always positive in this case. Okay.
Yeah, we can say that the negative part is always 0.
A negative what?
Part of the integral.
In the frequency space, it's a matter of the reference of energy we're choosing. So we're taking any additional energy to the free particle energy. Remember this omega is going to be now the free particle energy plus something, okay? So the free particle energy is positive because the free particle energy is going to be the solution to the Schrödinger equation with a plane wave. Okay, so this is going to be an extra energy due to the dressing of the particle. So this is always an additional something positive added to the free particle energy. Okay.
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 Thank you.
Okay, good. So one thing that we want to point out is, remember, I also mentioned yesterday that we could draw this diagram in 2 ways. Okay, so remember that we could have a tadpole like this. Okay, just so you connect between the drawings I'm making and the interaction, or it could be like this. Okay, and this is going forward in time, so this is going backward in time. Okay, this is what's the difference between these 2 diagrams? The choice I made of the interaction, what legs, how I label the legs of this interaction, right? You're going to have some nice exercises in the next homework. So here, if we label this as K, K, and L, okay? So this means I choose K here, okay? K here coming out, and L, okay, is coming out here and joining in here, okay? So this would be also L here coming out. Okay, here we do the opposite. So we label here K and K here, and now we label this as L coming out, L coming in, okay, and we join this, okay. So now this would be you can figure out that this is going to be the V. So we have the inputs are going to be the second 2 labels. So this is going to be the K in, L in, and this is going to be the K out, L out. So this is the KL, KL, okay? And if you do the same now, this is going to be R, okay? This is R and this is R prime in the matrix element, okay? So this is going to be the LK, LK, okay? But we know from the construction of the matrix element, okay? And I'm going to be particularly detailed here. So we have the B, K, L, M, N, okay? This is the double integral, dr prime, okay? So we have a K dagger R, KL dagger R prime. Then we have our Coulomb potential. Okay, phi M R phi N R prime. Okay, so you see that we can the difference between these two is just that in this combination, okay, in this combination you assign K. This will be the inputs, right? So in this first diagram, okay, so let's put this here, 1 and 2. So we're just choosing this M, okay? This is M is going to be K. It's on the R side, okay? And this M, N is going to be L, okay? And then on this side, okay, we have again this K is going to be K, and this L is going to be L, okay? And in the other one, we just swap R for R prime. So whatever was doing R now is doing R prime here. So K going in, going out in R now is going to R prime. So we just are swapping these two. So in the other case, it will be L, K, and L, K. Okay. But this is a symmetry. Okay. So these two are going to be identical, because changing the labels like this is like changing R for R prime, okay? Same as changing, going to be too fast, as changing R for R prime. If we change R for R prime, then what we're doing is a swapping, right? So we change this one here and this one here, and we obtain this diagram. So this integral will not be changed by changing R for R prime, okay? The R for R prime here, it just changes the sign here, but this is the modulus, so this doesn't change, okay? And then changing R for R prime gives me exactly the same integral, because there's no distinction between one integration and the other, okay? So this is a symmetry, okay? A symmetry of the labels, okay? So these two diagrams are going to be exactly the same. So I only need to draw one of them and multiply by a factor of 2 in the expansion, okay? Is this clear? You know how to obtain now the correct labeling depending on the diagram, okay? Just assuming always that you have this, starting from the basic structure of the interaction, okay? You have M, N, K, L. Okay, from here, then you take, of course, I mean, I'm using maybe too many times the label K, but imagine that these are all primes, okay? And then you assign K to this leg and K to that leg and so on, okay? And you see the integral. What essentially you are doing is assigning the K's to the R side of the label. So one of these is going to be the R side of the label. The other one is going to be the R prime side of the label, of the interaction diagram. Okay? Okay. Okay, good. So now we're ready to do the same thing for the tadpole, for the oyster. Okay. So let's do the same for the oyster. Okay. So let's draw something like this. Okay, so we'll do it a little quicker. Although you can play slowly at home. Okay, we have something like this. Okay, and in KT space, okay, although I won't be doing the Fourier transformation, you can do exactly the same exercise, and we'll put again the label L, the intermediate label there. Okay, and this is going to be now again the sum. Okay. Okay. There's one difference here, and I'll ask you at the end when I finish this, between the oyster and the tadpole. Okay. So you have the sum less L is smaller than KF. Okay. Then we have the integral between minus infinity and infinity dt. And then the first propagator coming in. Okay. This occurs at time t again. So we have k, and this will be a t1 and t2. Okay, so we have k and t minus t1. Okay, it will be the first factor. Then we have minus, and now we have lk, and I leave to you to show that this will be the lk instead of sorry. In this diagram, we have L, K, K, L. Okay? And this will be the interaction. So, okay, figure out. Okay, by drawing the, like the exercise I did in the previous section. Okay, then we get the minus I, G naught minus, and we get the L. Okay, and again we get T minus T. Okay, because this emerges at time t and is absorbed at time t. Okay, so we get the same factor here, and then finally we get G naught. Okay, K T2 minus T. Okay, so we have 1, 2, 3 propagators, 1, 2, 3 propagators, interaction line, interaction line. Okay, so this is a full expression. Okay, and in Fourier space, doing exactly the same exercise as we did in the previous page, then we get minus 1, okay, sum L smaller than KF, and then we get the I G naught plus in K omega squared, okay, and then we get minus I over 2 B L K K L. Okay, of course, if we do this the other way around, okay, so this would be for this tadpole, but we could have a tadpole for the oyster, but we could have an oyster like this. Okay, so this would be K, and now we would choose K on the R prime side instead of the R of the R side, and now we would have that the corresponding V is going to be KLLK. Okay, and notice that we're just swapping these two together, and that amounts to, okay, in the integral I showed before, amounts to changing R for R prime. And we know our integral is completely independent of that, okay? Okay, so this is the result for the oyster. What's the difference between the oyster and the tadpole? There's going to be a minus sign. Remember that we don't get now no fermion loop. There's no loop here. Okay? So no fermion loop, so we don't get the minus sign, and then this term would differ in sign because the fact that we don't have a fermion loop. But we do have the minus sign due to the G0 minus, okay, evaluated at the same time, okay, and T minus T. Okay, any questions here? Okay. So let me explain why we have this 2 here. This is a convention, okay, of Matux. Can anyone imagine why we have that 2 there? What have we neglected in the description of a fermion? What did you think will introduce a factor of 2?
Maybe if we don't want to count twice the fermions because they are indistinguishable.
No, it has to do with the property of fermions that all fermions have, which we have sort of thrown out here. So an electron, for example, what does it have? It can have momentum, right?
It's because of the spin.
Sorry? What other, it can have momentum, what else can it have?
For the spin?
Right, the spin. So we have forgotten about the spin variable. So the electrons can be spin up and spin down.
Spin down.
Right?
The degeneracy of the spin.
Right. So we not only have to sum over the momentum of the spins in this intermediate for the loop, okay? This intermediate loop that has label L, but we have to sum over the intermediate electron spin, okay? So here we should have another sum, okay, which is over spin, okay? So we could put like L less than KF and then put spin here, okay? And what happens if the interaction doesn't depend on spin? There's no spin dependence in the Coulomb interaction. The Coulomb interaction sees the same for an electron spin up or a spin down because it depends only on the charge, right? So this summation we can do, and this summation gives me a factor of 2. So we just count two times the fact that the electron, and you remember that the Fermi sea is filled up with a two spin orientation. So we fill every level below the Fermi level with spin up and spin down, spin up and spin down, right? So happens when I try to draw, lying down on a chair. Okay, so we know that the Fermi sea is being filled like this. So when we have a hole, okay, the hole is going to be either spin up or spin down. Okay, so we have to sum over those spin combinations. So that's why Matuk includes this factor of 2 here. So when you sum over 2, the expression is the simplest possible. Okay, so this factor of 2 cancels this one. Okay, and we are left with the simple expression. Okay, so let me just put the simple expression in the other page. So we have the oyster. Okay, and this is going to be canceling both factors of 2. You just get the -1 from the G0 minus, okay? And we get L minus KF, okay? And then we get the 2 Green's function moving forward. Okay. And then we get just the minus I V A K L L K. Okay. So that's it. So this is all there is to this is the Fourier space expression. Okay. So anyway, we have to do this this remaining sum. We have to do it, and we'll do that later. Okay. There's one point I want to make again about the meaning. Okay, meaning of omega, like was asked before. Okay, remember this is going to be the energy of the quasi-particle. Okay, it doesn't have to do anything with a single. It's not the free particle energy. Okay, it's not the single particle energy, but the energy of the electron now dressed. Okay, of electron dressed by virtual processes. Okay, so this is important because then when we go to Fourier space, the Green's function has a particular this pole form, right? So the Green's function in Fourier space has this pole form. So it's going to be omega minus E sub k plus I delta. Okay, and this is the energy of the dressed particle. Okay, as we have the free propagator is not dressed by anything. Okay, so it's just this is the free particle energy. Okay, and the poles occur when omega is equal to epsilon k, since we can take delta to 0. Okay, but when we now do the expansion for the full Green's function, then this will be an epsilon sub k prime, okay? And now that will be the omega will vanish, or the pole will be at epsilon sub k prime. So that will be now the energy of the quasi-particle, okay? So that's important to know. Okay. Yes.
In this case, we are considering the photon as the virtual particle.
That's also the language that is used also, okay? But the most frequent language is that this squiggly line I have here is some intermediate, okay? Intermediate particle, intermediary, okay, particle, which is the Coulomb field, okay? How we describe the Coulomb field, we describe it in terms of photons, okay? And then when we have some, you know, the weak and strong interaction, we have other, yes, those are intermediate bosons, right? Okay, okay. So we would this line would represent a photon in the case of the Coulomb interaction, and a gluon or a Z boson for the other particles interactions inside the nucleus, for example. Okay, so this is exactly the same mathematical picture. Okay, okay. So let's now summarize. Okay, summary Feynman rules. Okay, so let's try to make this a nice summary here. Okay, so in k omega, and we now that we know how to transform from kt space to k omega space, remember, okay, so k omega space is going to be useful whenever our interactions are translationally invariant, okay, so that k is a good quantum number, okay, so we can just go and also k omega, both of them are going to be good quantum numbers, okay? So we have now in k omega space, we have g plus of k omega, okay? So, one second. I had very good intentions here, so this will be the space here, space, okay, and here we have the diagram, okay, and the diagram for this will be then the double line, okay, and we'll have a single label for the diagram, okay, and we also have the I. Okay, although we won't see any of this, maybe one of the topics that you might choose at the end of the course is, for example, determining the ground state energy of a Fermi system using the Green's function expansion, and you will get to see the expansion now for G minus instead of G plus. So this will be a propagator now going in the other direction, K and omega, okay? Then we have the free particle propagator, so we have G naught, again in K omega space. And this we know exactly because when we draw the expansion now in terms of the ingredients of the soup, okay, we have to know what those ingredients are, and this will be this guy, and the picture associated with that free propagator is that one. And then we know now also about these advanced propagators, okay, which will have the same expression, but now minus I delta, and this will be a propagator in this direction, okay. Another prescription we have now loops in our diagrams. So this will be just -1 for k smaller than kf, and 0 for k larger than kf, okay? And this will represent any closed loop, okay? Or something, yeah, any closed loop like this, okay? You could also have some more complicated, so you can imagine, although we will not address diagrams that have such complicated loops or attempt to calculate them, but you could have something like this. Okay, so if you can follow through the arrow like this, okay, this is a fermion loop also, okay, fermion. So just any closed loop will be assigned a factor of -1. What else? And then we have the interaction, okay, and then we have the interaction. The interaction will be -1 over 2 KLMN, and this is represented by the interaction lines. This KLMN in and out. Okay, and remember this is a spin factor. Okay, that gets cancelled whenever the interaction is spin independent, then we get this factor of 2 cancelled, okay? Okay, cancelled when interaction spin independent. Okay, so that's the, and the final ingredient of all this is, yeah, you have to, you sum over all intermediate labels. Okay, so you remember that K for, in particular for a solid, is going to be a discrete sum. So you sum over K's, okay? And you integrate over intermediate omegas also, because now you can imagine that we're going to have intermediate omegas, okay? So we consider the energy continuous, while the K vectors can be discontinuous or discrete, okay? Although I'm going to make some comments of how to convert later, how to convert sums to integrals without, you know, having any problems. Okay. So the next topic is now, okay, now using this new power that we have. Okay, so the Hartree approximation. Okay, now we're going to make contact with some fun but somewhat artificial exercise that we did before. But now you'll see how we can apply that technology to the Hartree approximation. Okay, so remember that we always need to do, let me change the pen here, okay? We always need to do infinite sums. Okay, in order to obtain a simple pole, okay, to describe quasi-particles. Okay, so but you know that the mess that I showed you before, remember that we have a lot of different diagrams here. Okay, so we're inspired, so we can have the tadpole, then the oyster, then the double tadpole, then the tadpole oyster, then we have this, what we call the polarization diagrams, and we can have, you know, a bunch of very complicated diagrams. And let me show you just a few that are actual diagrams, the valid diagrams, okay? So imagine that we could have first, okay, we could have the polarization diagram, which we already drew. Okay, and we have the particle hole here. But we could also have something like this. So again, let me draw the interactions first, and then the other interaction line here. And this can come out here. Okay, and then following this line, you can have a propagator here then. Okay, and then this goes back here. That could be another diagram. Okay, or you can have some very complicated monsters like this, for example. And you will analyze them in the homework, whether they are valid or not. Okay, so you have one line going in, and then you can have another interaction. So this would be a second order interaction. Okay, and you can have something like this. and then coming out here, okay? And then continuing here. So this will be a second order diagram, and so on. So you can have many more complicated things, okay? So each of these is going to be a distinct integral, and you'll see that just by solving this guy, which is the most complicated diagram we're going to solve, things get really, really complicated, okay? And nature saves us again, because we can identify a subseries which is going to be much simpler to solve and which is physically significant. So this will be a third order diagram, okay? Okay. Okay, so let me make a final argument in the class. So we'll go over a little more than 15 minutes because we started a little late, okay? So, so the philosophy will be, we will identify a subseries of diagrams which will be more important than the remaining ones. Okay, so what do I mean by this? So let's go. We have to go to the form of the matrix element. Okay, so the matrix element with which we will build the interactions in second quantization. So let's look at this guy, for example. Let's look at the integral for this guy. Let's see if you buy, and we're going to compare it versus diagrams which have other combinations of labels. Let's say this, where K is different from M and L is different from N, okay? So let's compare which of these two is going to be bigger. So that's going to be now our criterion to select diagrams in that expansion and to eliminate monsters and just create, you know, little monsters from known pieces that we already know how to solve, okay? So let me draw first this KLMN integral. So the first one is going to be, and I'm going to be try to be economical, just putting the labels, okay? K, L, prime, and then we have the Coulomb interaction. This is an argument that's going to be useful for later in class, also for when we do tight binding approximations. And then we have M. One second. Okay, so let me draw this one first. So K, R, and L. And we've got a conjugation here. Okay, so this is the first integral. Okay, so this is going to be this one. Okay, and the other one is going to be now phi, and we start the same way, KL.
Teacher, in
Yes.
this case, I'm going to consider only 2 particles or 1, or we're going to consider more than 2?
So we have 2 particles. So this is a 2 particle. Okay, so this is so remember that we when we wrote this is a 2 body interaction, right? So this is
Yeah.
going to be involving two particles. One, the two labels coming into the interaction and the two labels coming out of the interaction, okay? So it's a two-particle interaction, okay? So
Yeah, for future, I mean.
For what?
For the future, if we're going to consider more than two.
No more than two. I mean, remember that we have, our brains can do better things than consider such complicated processes, okay? So
Okay.
only at most two particles, we can do most of the physics we need with two particle interactions. Even CERN does not do, does not do higher order. This will be, for example, in the context of particle physics, then you would have to go beyond the standard model to do the quark gluon plasma type problems. Okay, so this will not concern us. So if there are higher order interactions, we will deal with them in other ways. Okay.
Okay.
Okay. So we have these two integrals. Okay. So nicely, right. Okay, so let's compare these two integrals. And I'll show you which one of these is larger than the other. Okay, so we have KL, KL. Remember that this is going to be the tadpole. This is going to be the tadpole. Okay, and this is going to be some other generic diagram where this relation between the labels is true. Okay, so let's look at here. So you have, this is phi of KR, and this is phi of KR. Phi of KR star, phi of KR, okay? So these two, if you, let's suppose you were doing the integration over R only, okay? So these two, if we integrate over R and ignore the V, what do you think will happen? What do we get? If we integrate over R and the V was not there, what does it give us? We have the same label here, and we have the same position label.
Delta?
Right, so we don't get a delta because already K is equal to K, so we get 1. Okay? K, it would be a delta if this K was different from this K, right? But this, they're both the same, so we just would get 1. And also, this is also the same if we do the integral over R prime, because L is equal to L, phi star, so we get another 1. So in the absence of this potential, this integral is huge. It's as big as it can be, okay? And then, okay, then you get, the effect of the potential. This can reduce a bit the size of this, okay? But it's already starting from a big value, okay? So it's a big value, then we can have a potential which has positive and negative parts, right? So this can be big negative and big positive because of the potential, okay? But now let's see what happens to this integral. So this is here, let me, so that you don't get confused here, this is M. So here we have the opposite effect. Now we have K and M here, okay, at the same R. So if we were to integrate and K is different from M, okay, and this would happen for some other diagrams we have in the expansion, then this will start from 0 because this will be delta Km. K is different from M, so this will be very, very small, okay? The same for this one. L is different from N, so this will be very, very small integral, okay? It will go to 0 as we integrate over the whole domain. And the only thing that takes away from this 0, from this going to 0, is the potential. So the potential, so imagine, for example, when this function is finite, this is 0, or this is very small. And when this is very small, this is very large, okay? So the potential sort of saves this integral from being very small if this is the condition. Okay, so with this argument, this is going to be much larger than KLMN. Okay, do you understand? Okay, so if these two labels are the same, this integral will be very large because it starts from the orthogonality relation. So this will be just 1, and this will be another 1, and then it gets modulated by the potential. In this case, it starts from 0. This is essentially 0 in the limit that we integrate over all the domain. And this will be 0, and then the potential sort of lifts up the value of the integral from 0, from a very small value. Okay, so the diagrams that involve k different from m and l different from n are going to be very small to start with. And these will be very large to start with, okay? And then they get modulated by the potential. Do you find this argument compelling? Do you find it understandable? So this is just on the basis of the values of these, of the magnitude of the interactions. And remember, this is going to be the magnitude of the second quantized form of the interaction, okay? So these interactions are going to be much more important than this, okay? Okay, good. Tadpoles. Rule. You know this expression in English? I'm sure you've heard it in seeing your favorite series in English. Okay? Tadpoles rule. Okay? So that means that we could take that this diagram, the tadpole diagram, taken to infinity, okay? The tadpole is in principle dominant. So instead of taking all these monster diagrams that I drew before, okay, instead of taking all these monsters, we can imagine a series expansion just in terms of the dipole. So we have the propagator is going to be the G naught, okay, plus, and then you're going to have the tadpole, okay, plus the double tadpole, okay, plus the triple tadpole, and this all the way to infinity. Okay, so first order, second order, third order, okay, to infinity, okay? So we assume and we neglect, and we neglect other contributions. Okay? The nice thing is that we're now going to be able to do an old trick. Remember, this is all in k omega space, okay? Okay? And then we can do a trick that we know. So we extract, we know that this is just algebra, okay? Algebra. No integrals there. So we can extract from here a propagator, and then this will be, okay, a 1 plus, and I made a mistake there, okay? So then we have a, okay, plus, okay, so on. So notice that here we have a tadpole propagator, tadpole propagator, tadpole propagator. Then we have tadpole propagator, tadpole propagator, tadpole propagator. So this is the second power, okay? So this will be squared, and this will be cubed, and so on, okay? So this should be familiar to you now. Okay, what we did, plus the 1, okay? So we can sum that series. This is a power series, so now we can have the propagator multiplying 1 over 1 minus, and then the tadpole. Okay? And then we could just remember that these are just products of things, right? So I can divide by this propagator here, and then we get propagator to the minus 1 minus. Okay, I just remind you that this has this label L inside, okay? So this will be the final result for an infinite subseries of this Green's function. Okay, so next class we're going to translate now this result using the Feynman rules, and you see that I don't have to do this integral and this integral and this integral. I just do this single integral here, and we obtain the full result. Okay, so that's the beauty of this, and now this result is really going to be meaningful. It's going to be the Hartree approximation. Okay, and that's the first thing you do when you study either electron gases, or you study multi-electron atoms, or you study some mean field approximation of the nuclear interactions, for example. Okay? Okay, any questions? So you see we can also do the Dyson argument with this. So we could, for example, substitute this whole series with a double propagator here, and we would obtain exactly the same. So we can, this is another way to derive this result I have here, okay? So the Dyson argument is general, okay? I recommend that there's a series of interviews to Dyson, which is very interesting because, let me just put the recommendation here. Recommend videos on YouTube. So you're bored, okay? Dyson interviews. Okay, so this is the guy that developed these techniques, okay? And he, this guy interacted with all the famous guys, Fermi, when they were alive, Bethe, okay, and Feynman. So he says very interesting things about these guys, okay? Especially when Feynman was developing this diagrammatic technique and how he solved many of the problems that, Feynman didn't know how to solve, were solved by Dyson, and, the impressions of Bethe and Fermi about an Oppenheimer about these new developments, okay? Very, very interesting interviews. Okay, so if no questions, so we're finished for today. No questions? Okay. So I hope the connection is fine. Okay. So please let me know if you have any other difficulties with the homework, okay? And so that we can set the new date for the turning it in by next Monday. Okay?
Mhm.
Okay, good.
Thank you, teacher.
Okay, see you tomorrow then.
See
Bye.
you.
See
Bye.
you.